Hello, everyone. This is Joe Armstrong. Just wanted to start the broadcast here to open up the lines. We got a lot of people joining right now, of course, top of the hour, and everybody's just hopping on. So we're just going to give a minute for everybody to get on, and then we'll get started, okay? So, guys, I shared my screen. Can you all see that now? Neil, Ralph,
yes.
Tim? Yep, okay, thanks.
You're now showing your wiki, right?
Yes. So I'll go ahead and, yeah, so the wiki's up there now, and just because, Ralph, I know you got a lot to talk about, so let's go ahead and get started here. Again, welcome everybody. This is Joe Armstrong and the Power Systems Virtual User Group webinar for September. I always have to glance over and make sure I'm in the right month on my calendar here. So today we got a lot to talk about today. Before we get started, I have a few things to cover. You'll see here I have the Power Systems Virtual User Group Wiki. This is where I keep all the information. There's a couple of things I want to talk about, and up here I put upcoming events on the wiki, usually education-related kind of stuff, and there's 3 of them I want to mention before we get started here. One is this IBM and Brocade Roadshow information. So this is a set of local events, guys. So this is the, if you take the link off my wiki, you'll get this, and it's a little flyer for it. And these are the cities that it's going to be and the dates it's going to be in them. So if you're local to these cities, New York, New York, Seattle, Washington, Capel, Texas, Dublin, Ohio, or Markham, Ontario, if you're in one of those areas and you want to join this, it's a great day. I was at one in Chicago a few weeks ago. The little agenda is over here. We're talking about some Power 9 stuff, some Flash stuff, general power, future, and some Brocade things. So, and a nice reception afterwards. So, feel free to join, register for one of these cities. I'll actually be I'm scheduled to talk at the Seattle, Washington one. So if you're there, come and say hi to me. It'd be great to see you. So that's that. The next thing is this Health Systems Power 9 Power Hour. It's October 24th. This is just a webinar. I usually don't talk about, you know, third-party type events that are going on. In this case, I'm going to be talking at on this webinar. So if you take this link, you'll get the registration for this. So feel free to do that. And the last thing, and the thing that I'm really most excited about, is this IBM Technical University. So the IBM's TechU, the next one is October 15th to the 19th. It's Hollywood, Florida. Couldn't be more excited about going to Florida again. I have a promotion code for this. So if you use this code, TUHVUG, so it's a Power Systems VUG specific code, you'll get a discount. So this is like the super early bird discount. It's $20.95. I think now the cost of the thing is $24.95, but this discount won't expire. So feel free to do this. And I can't talk enough about how great the TechU is. This is the best conference I think IBM puts on for technical people. Just a ton of things there, and most of the people that I have, I think, on today might be there. So we'll talk about that. So with that, I think I want to get to our topic for today. So today, we are talking about the Oracle database on IBM Power Systems with AIX and best practices. And I love best practices webinars and information because there's so much practical information in them, stuff that we can use, and a lot of things that you might not know about, and it's not covered necessarily in red books and stuff like that. So great information here today. You'll see here again on the wiki, I have the presentation materials here, a little link to the presentation materials. This is what Ralph's going to cover today. After the webinar, he's got kind of an expanded one that I'll put up there again after the webinar. So feel free to do that. And also after the webinar, I am recording this. I'll put a YouTube replay up here as well sometime after the webinar. So with that, let's get to our topic. Ralph Schmidt-Danner is going to be our speaker. We also have 2 of his colleagues, Tim Spencer and Neil Rudnick, on as well. They're going to be answering questions in the background. So feel free to type in your questions and and they'll get to them. And this is great because we got real expertise out there talking about it as well. Ralph has over 26 years of experience in the IT industry. He's currently executive IT specialist with what we call now our Washington Systems Center. Used to be our ATS group, Advanced Technical Support Team. He works with Oracle at IBM. He spent most of his career focused on very large database environments, testing them, designing them, troubleshooting for high performance, high availability, and a near zero data loss disaster recovery. Ralph's helped customers in the financial, telecommunications, utility, retail, manufacturing, all kinds of industries to choose the appropriate database, the infrastructure to run that database on, to meet the business requirements with databases up to 100 terabytes in size. So he's really done the whole gamut of things. Most recently, Ralph's evaluating and implementing technologies to provide database as a service to customers, kind of a big deal these days, on IBM Power Systems, and it includes both Oracle, which we're going to talk about today, and other open source databases on Linux on Power, which open source databases are really coming on big. So now Ralph has told me, he's probably getting tired of me talking because he's told me he's got a lot of material to cover, everyone. So with that, I'm just going to pass it over to Ralph now and let him get going. We do have a poll to put up when you get started, so I'm going to let Ralph kick that off, and then we're going to stick a little poll up there and get a little feel for the audience. So take it away, Ralph.
Yeah, thank you, Joe. So thank you everybody for joining this call. I hope it will be of interest and has some small nuggets you have not heard before or you have not been that familiar with. As Joe already indicated, I have quite a few slides. Some of them I will only go over very high level, but the slides are already available as a PDF, and I will provide a more extended version after this call with some additional background information. So you want to go back after the presentation, get the latest PDF downloaded and look that over again. So Joe, how do we get the poll up?
All right, so I am putting the poll up now, and the screen will change. Everybody will see the poll now. Here's the poll. What role do you have? Here's your options. Go ahead and select one, and I can see you know, how many people have done it. When we get kind of slowed down on this, Ralph, then I'll let you know.
Okay. So I've done this kind of presentation for I'm not sure how many years. But one of the focuses I typically have is to get system administrators, database administrators, and storage administrators together into one room and hear the specific message, okay, what does it mean to have an Oracle database on AIX? Quite often I find that those teams do not really talk to each other. They do not have the same vocabulary, and from that perspective, it's definitely a challenge to get the communication going and really figure out what the dependencies are. And I just find that I have a small challenge here, so I'll keep up the poll because I find that my slideshow decided to use timings and it's happily scrolling forward in the background. So what's the status of the poll?
So we have 80% voted. It's really slowed down, so I'm going to go ahead and just show the results then. Let's see here. If I do this and then share. Okay, so here everybody should see the results of our poll now.
Except me.
Except you all. So it shows, what it's showing here is that about 56% are sysadmin, 2% storage admin, 20% database admin. We have 3% managers on, and then 18% other. And somebody typed in a suggestion that we probably should have had like architect in there as well. Maybe that's some of the others are architect.
Okay. Okay. Thank you, everybody.
That would be, I think, about 83%, and we have 440 people on. So, you know, about 350 or so.
Okay.
So I'll go ahead and hide that, Ralph, and let's see, and we're back to your screen now, Ralph. It says learning objectives at the top.
Okay, so that's what I already talked about, and really just to repeat here, what is the best practice on Oracle data on database on AIX? How do they work with each other? What are the impacts? Especially focused on memory, CPU, and I/O, and depending on time, let's see how deep I can get. Some of the typical pitfalls I've seen at customers, and a little bit about AIX tuning parameters. Luckily, with latest AIX releases, there is not that much you need to actually change, but also about what to do or look out for if you evaluate performance, need to do tuning and optimization. So I will talk about these areas. Focus will be memory, CPU, and I/O, and the other three at the bottom, network, patches, miscellaneous, are as time permits. So one sales slide, that's the only one in this deck, I promise. And this is the lineup of our Power servers. And the main point is, if you look at the blue circled physical servers, P8 and P9, they all can run AIX, and therefore they can also run Oracle database on them. The one in red are Linux only. They are not supported to run an Oracle database. So Linux on Power. So let's dive into the more technical stuff. So I thought I'd start out a little bit with memory pages in AIX. Pools, pages, free list, use list. There's a lot of different terms. Some of them I may refer to later on. But AIX is very flexible in how memory is managed. On a high level, you have typically free lists and use lists for different page sizes. AIX utilizes or supports on current power processors 4 kilobyte, 64 kilobyte page sizes, which are the main page sizes, as well as 16 megabyte and 16 gigabyte page sizes. And I'll talk a little bit later about where and how they're used and how they could be configured. Key point here is that AIX does a lot of under the cover migration between page sizes, especially in the arena of 4 KB and 64 KB pages. The process you're responsible for that automatic migration is the PSMD, so the page size management daemon. And you may have sometimes seen that in your, for example, N1 data or Topaz data, that process can utilize quite a bit of CPU. We also have some automatic migration of 60 megabyte, pre-configured 60 megabyte to 64 kilobyte pages, and I will talk about that later. And 16 gigabyte are somewhat special, but they can be utilized for an Oracle database. If you look at the 60 megabyte pages for used, you notice that there are two different lists. I just want to point out later on when I talk about multiple page size support that the dynamic aggregation of smaller pages into 60 megabyte pages is handled and managed on a different list than the pre-configured 60 megabyte pages. So just to be aware of that. On this slide, it's an eye chart. When you get the full handout, for each of these events, you get a description of what I did. And just, there's exactly one point where I manually made a change, and I leave it up to you to figure out which one it was. And when you get the handout, you will see that. But this really shows, this is based on N1 data with a capital M parameter on how memory is allocated in page by page size for the different lists. So in AIX, there are two main groupings of memory. One is computational, and the other one is file system. And if you're not familiar with AIX, I assume everybody here is, but there are other Unix flavors where memory management is differently handled. With AIX, AIX tries to utilize all the physical memory available on the server, except a small sliver to handle actual current memory requests. So it's not atypical in an AIX environment to see the amount of free physical memory to be very, very low. Note that, so file cache pages, if, for example, Oracle database needs more memory, you start a new Oracle process, and there's not enough memory on the free list, AIX will start stealing pages from the file system cache. And the process doing that is the LIUD daemon. I show you on this slide the different parameters which influence the behavior of this process. Key point really is that in AIX, physical memory is split up into multiple memory pools. Each memory pool has 4 KB, 64 KB, 6 megabyte pages. And the LIUD really works mostly with the 4 KB pages, but could also work with 64 KB pages. So per memory pool, we have an LIUD daemon, and it evaluates, okay, if my free pages go below min free, I need to forcefully free up used pages. And default behavior in AIX with current releases is to only go against file system cache pages. If they are not sufficiently available, LIUD will also go against computational pages. So that's something you do not actually want to have happen. And as soon as LIUD for every memory pool finds that it has sufficient free pages, 4 KB and 64 KB, larger or equal to max free, the LIUD daemon stops. So if you see the LIUD going on, you know that you have memory pressure on your system. If your file cache is also pretty low, means close to min per percent, that means you are very likely close to paging space. I've also already mentioned that we have min-free and max-free values up per memory pool. So the overall amount of physical memory AIX tries to keep free all the time is min-free times number of memory pools. And that is for 4 KB and 64 KB free lists. And as I already mentioned, LIUD will stop if sufficient free memory is available. By default, the current AIX 6.1 to AIX 7.2 values are typically sufficient to support the workload. I show here if you find that you are running frequently out of free memory because you have significant variance in your workload, means the physical memory requirements vary significantly, then you may want to adjust values min-free and max-free, as I show here on this slide. Now, I already mentioned LIUD and paging. So if you run out of free physical memory, your file system cache is already kind of exhausted as well. AIX, like basically every Unix system, will start stealing pages and write them to the paging space. That's a specific area on disk to temporarily store paging, computational pages of a program onto disk. Note that file system pages are never written to the paging space. It's really only computational pages of programs. In the context of an Oracle database, the goal is really to have zero paging to paging space. The main reason for this is that if paging space is allocated, so if AIX writes pages to the paging space, that space is never released unless the owning process actually terminates. In the context of an Oracle database, those processes typically live days, weeks, months, depending on how often you restart your database. So even a small amount of paging can over time result in very significant paging space usage. So Oracle database, you do not want to see paging to paging space. I provide here at the bottom in this small table a rule of thumb of how I typically suggest to configure the size of the paging space in an Oracle database environment. The half the physical memory plus 4 GB is the Oracle default recommendation, and I put a cap on it for larger memory environments because, for example, you have a 1 TB memory system, 200 GB of paging space is already quite a bit. And if you reach that paging space, you will likely end up with significant performance issues, up to database instance being terminated by AIX as the largest memory user because you're out of paging space. So if you see paging, you need to very, very quickly address it, and the paging space is only a short-term fail-safe to give you a little bit more time to react to it. One of my favorite topics, and I'm still seeing too many customers not really aware of it in the context of AIX, is JFS2 inode and metadata caches. Databases typically have a relatively small number of files if they are running on JFS2. If they're running on ASM, the only files you really typically work with are the Oracle binaries and log files. Now, AIX has, in the context of JFS2, 2 caches. One is for inodes. Each file has an inode, and as well as metadata cache. Basically, the metadata of the JFS2 file system. How are blocks allocated to specific files? AIX default maximum size for the inode cache is 5%. For the metadata cache, it's 2% of physical memory. So 7% of physical memory is potentially allocated to those 2 caches, and it's not pinned, and it's pinned and cannot be paged. So I've seen quite a few customers basically complaining, oh, my database is up and running, and AIX is using more and more physical memory in the system area over time. And those customers run an Oracle database, but they also do things like importing on a regular basis small files in a pretty larger number, or exporting files. So new files are created, new inodes are cached. The behavior of these caches is that they will grow to their maximum size first before entries are reused. So that means can be a very significant physical memory user, and you want to potentially, in a database environment, significantly reduce those cache sizes. And I provide here a high-level rule of thumb of how much memory you will need for 1,000 file inodes. You can run df-g, which tells you each file system how many inodes you have. You can sum it up. You can divide it by that number, and that gives you an idea of the minimum cache size your system actually would only need. And typically, especially in larger memory environments, you can save significant physical memory for those caches by adjusting those parameters. Another feature which becomes more important with the ever-growing database sizes is limitations of how many entries, so segment lookaside buffer entries, the power processors can support. These SLB entries are utilized to support translation of virtual addresses to physical addresses, so they are a critical piece in the performance of processes with larger memory footprints. So in this case, specifically the SGA, which can be terabytes, hundreds of gigabytes to terabytes in size. With a power processor 7 to 9, you have only 12 processor slots to support a segment lookaside buffer. By default, that's 256 megabyte per buffer. So you can only, from a virtual address space perspective, directly access 3 gigabyte of physical memory before you ran into SLB faults, which are expensive from a processor and time perspective. With large segment aliasing, instead of the segments being 256 megabyte in size, they are 1 terabyte in size. So that feature allows us to map 12 terabyte of virtual address space to physical memory. And therefore, you typically would not get any of those SLB misses when you access memory. The good thing is, with AIX 7.1, 7.2, that is already enabled by default for shared memory. If you're still running AIX 6.1, you want to set the VMO ESET underscore allocator equals to 1. And also need see the bug for 11203. We recommend not to enable this 1 terabyte feature for unshared memory, as I show you at the bottom. Another feature which is newer or relatively new is Dynamic System Optimizer. If you have AIX 6.1, 7.1, then it was the key feature of this is the mixed page size segment, and it was chargeable. And you had to pay for the ASO.DSO file set. Now with AIX 7.2, that feature is actually included in the boss.ASO file set. So if you have running AIX 7.2, you have that feature for free, but by default it's disabled. So what does it do? It takes, for shared memory, so for your Oracle SGA, it allows AIX to take 4K and 64KB pages and aggregate them together to 16 megabyte page size. And that's all dynamic transparent to the database. Benefit is you significantly reduce the virtual memory management overhead the processor encounters by managing large SGAs. At the bottom of the slide, I show you how you can activate it, and the key option to get the mixed page size support activated is the large underscore page equals on. So I did a little bit of a small test, and there are a number of tuning parameters which are a little bit too deep to go into at this time, but I used the most aggressive setting and started my database, and you can see that it took a while for AIX to even start converting pages, but then I converted about 1 terabyte of pages, and you can see that it has some CPU overhead. It's not that high, 0.2, 0.3 of a physical CPU, but you can see it in the N1 graph on the left top that what the impact was. And at the bottom left, I show the command on how you can determine that it's actually working. And you see segment areas, and if you see mixed segment size, so in this case M stands for 64 KB pages, L for 16 megabyte pages, and you can see that the top segment only has 64 KB pages, whereas the two lower segments both have only large pages. So they were actually migrated from 64 KB to 16 megabyte pages dynamically. When you shut down your database, all those 60 megabyte pages, of course, disappear. So there is a clear difference between pre-allocated 60 megabyte pages and those dynamically created ones. Another area with memory is how fast can you access memory? And in the table at the bottom, I show you what we call local memory, near memory, and far memory. And if you go from local to near to far, the access latency to read memory content increases. With every new generation of power servers, we have improved on especially the near and far access latency. So Power 980 especially has, so the E980 has a significant improvement in that area. But this is at the top, at the bottom, really gives you an overview of where the memory would be. And then one other note I'd like to make is Power 9 is always a single chip per socket. So it has an impact on, you can use Oracle standard licensing on 2-socket E924, for example, and could run standard edition, which you could not do with Power 8. So if you want to look in your LPAR, how is my memory and physical CPU, or my memory and CPU relationship actually currently implemented? Here an example. This is from a Power 8 dual chip math modules, and you can see that the first socket has 2 chips. Each chip has its own memory controllers. Memory is locally attached to it, and we have the CPUs 0 to 31 and 32 to 63 mapped to that socket. If you go further down, you see, okay, we have additional sockets where memory and CPUs are allocated. But if you look at the bottom 3, you notice that you have logical CPUs where there is no local memory configured. So this is a configuration which is, or can have a very, let's say, quite significant performance impact. 15%, for example, if you utilize processors on SRAM 3 to 5, because for those processes, every memory access will be a near or far, or will actually be a far memory access for most of them. So can have a very significant performance impact. That was especially prevalent with Power 7. With Power 8, the impact is lower, and with Power 9 even more. But you want to definitely check your LPAR. Does it look like this, or do you get good distribution of CPU to memory, and as local as much of it as local as you can get? So how can we help the hypervisor who is responsible for distributing and the mapping of virtual CPU, logical CPU to memory on that level? How can we help it? One thing is, if your workload doesn't need that many CPUs, don't over-configure them. If you can fit into a single socket or a single node, try to keep your CPU number in that realm, and also be careful of over configuring your max CPU you can dynamically grow to. In the context of shared CPU AirPars, it's very important that the number of virtual CPUs is also kept within reason, and that your entitlement should not be more than about, or should not, so the number of virtual processors should not be more than about 2 to 3 times the entitled capacity of that AirPar. My best practice would actually be to try to keep it less than 1.5x. The problem is if you define too many virtual processors compared to entitlement in an environment where you have a lot of other workloads, other AirPars competing for resources in the shared processor pool, you can encounter quite significant hypervisor overhead. Trying to schedule virtual processors just to have them being very early preempted because you ran out of entitlement. So that's the underlying reason why we do not want to have AirPars where the number of virtual CPUs is above the ratio of at most 2 to 3 of entitlement. Another important rule is going back to mapping of memory and CPUs, do not over-allocate memory. And that does not only mean desired, but also what you specify as maximum memory available to dynamically grow the AirPar 2. The hypervisor looks at the memory at the maximum value. And if you specify a very large value, it may decide to spread out your AirPar much wider over many more sockets or nodes than the number of CPUs and your desired memory may indicate. So be very careful with just picking a very large value because you may think you may want to have it, but not in the foreseeable future. So try to keep it within reason. And the last bullet point, of course, it's I think it's a given. Keep your firmware current. IBM is always improving hypervisor algorithms, features, and if you are not keeping current, you're not getting all the benefits of these improvements. This is my favorite slide because I don't really have to say much to it, because the standard parameters in current AIX are a very good starting point to run a database. So there's very little to change out of the box when you deploy a database. So far I talked quite a bit about the AIX side. Now let's look a bit more. Where does Oracle actually come into play from a memory perspective? Oracle has 2 key memory areas. One is the system global area, or short SGA, which contains things like the shared pool for process SQL statements, the in-memory area, if you utilize the Oracle in-memory feature, we do log buffers. Typically the biggest area, if you're not using in-memory, is the database buffer cache. That is where the database caches its data to reduce the amount of physical I/O to disk. So SGA, one big chunk of computational memory. So from AIX perspective, that is computational memory. The other area, which is also under database control, is made up of the sum of all these process global areas. Each process has its own private area, the PGA, and you can see here the subset of typical Oracle processes listed. If you look at the bottom left, this is where you have, for example, your database connections. So users coming in, each of those connections get their own process, their own PGA, and they can, depending on your activity, the PGA memory requirement can vary quite a bit over time and can make up a significant amount of physical memory usage in your Oracle database AIX environment. So again, SGA and PGA, those two memory areas together are the majority of where Oracle allocates memory for. What other stuff is memory being used for in AIX? Of course, the kernel, right? It needs its own space, and already mentioned SGA and PGA. Then, if you are utilizing JFS2 file system for your Oracle database, of course, if the file system cache could be playing a role. If you're doing archive logs, export, import files, backups, binaries, two files, they are typically also cached. So file system cache in the Oracle database still plays a role, but it's typically relatively small. So from a system admin perspective, just to summarize, you want to keep your computation pages in memory. That means you need to configure sufficient memory to fully support your SGA and all your PGA requirements. And if those significantly vary over time, you need to make sure that you can support your peak requirements. And of course, the AIX kernel by itself, then the J2 metadata cache and inode caches are also playing a role here. So if those grow over time and you allocated 90% for your PGA, SGA, and they grow, you may run unexpectedly out of memory after a week or two, depending on how much you're doing with JFS2 file system. So be aware of that and adjust those parameters. So memory allocation management has changed with Oracle over time. So I want to go a little bit over the parameters we use, which were available or which are still available, and the impact. So it's Oracle 10G, which is pretty dated, but I'm still seeing it quite a bit at customers. You could only dynamically control the SGA area. So Oracle, you can specify, okay, I want to have that as a target memory size. I can specify also a maximum, and then Oracle under the cover adjusts key memory size areas. So before 10G, you had to specify everything manually, so DB cache size, shared pool size. With 10G, you can tell Oracle, okay, just SGA size, this is what you should use, and Oracle adjusts accordingly and can rearrange within the SGA as needed. That parameter is still available today, and I would still suggest that for most databases, you specify, you utilize those parameters like DB cache size to specify a minimum you want to guarantee for your database. A side note, if you're running or if you're utilizing log SGA, Oracle will allocate the physical memory specified in SGA max size at startup. So just something to keep in mind. With 11G, Oracle has expanded the automatic memory management, and we now have memory target and memory max target. And memory target now includes both SGA and PGA memory areas. If you use memory target, the default distribution is 60% of memory target is given to the SGA, 40% is given to the PGA. We have seen some challenges at customers where Oracle did this evaluation and reshuffling of memory between SGA and PGA quite too often. It's a quite disruptive activity. So at the bottom, I show you some MetaLink node you want to read into if you see some of these challenges. With Oracle 12c, we now also have the option to actually limit the PGA size. So with 11G and 10G, there is no real, let's say, hard limit. So if more and more connections came in, or somebody did really large sorts or extremely high parallelism, you could run into very large memory areas allocated to PGA and basically end up with out of memory and paging. Now the Oracle 12c allows you to limit the amount of memory allocated to the PGA, and the database will actually actively kill sessions to stay within that limit. Oracle 12c also added the in-memory size, so the support for the in-memory feature. And with 12.1, that is not dynamic, so you have to reboot the data, restart the database to change that size. With 12.2, you can dynamically increase in-memory size if you want to. From my perspective, I typically recommend to still utilize, even with 12.2, SGA target, SGA max size configuration. There are some other side effects that I will mention later on. Instead of a memory target, memory max target. There are exceptions where you have environments where you have significant variance between, for example, batch workload overnight and interactive workload over day, where requirements for SGA and PGA sizes significantly change, and you cannot support both SGA and PGA sizes at the maximum values within your physical footprint. So I would still start out typically with SGA target and SGA max size, and then the corresponding PGA aggregate target parameters instead of utilizing memory target. A side note, memory target, memory max target are not hard limits. And what I saw with 12c is that Oracle has some interesting idea of counting paging space as available physical memory. So if you look at the bottom left, you see that I set memory max target, memory target to 210 gigabyte. My physical memory in the server was about 260 gigabyte, and Oracle actually set the SGA and PGA to utilize 263 gigabyte on the same system. So be aware of this. It can actually lead to paging space. So we have at least, I've run into one or two customers where we ran into this problem. So be aware if you run 12c that there are some unexpected behaviors. Now, one other parameter in Oracle databases which has a significant impact on how memory is used, and that is log SGA. Log SGA allows the database to pin memory so it cannot be paged to paging space. The problem with it is that it pins all memory, so it's really allocated up front. You start the database and all the physical memory is pinned. So it will also utilize or pin SGA max size. If you do not set SGA target and max size the same, you actually have physically allocated memory which cannot be used by anybody. 64 KB pages will be used with log SGA equals false with 10.2.4 and later by default on AIX. One exception, if you're using active memory expansion, then at this time it's still 4 kilobyte pages. So AME has a negative impact here. The support of 64 pages, I believe, is still currently being evaluated. If you have manually configured 60 megabyte pages and you start up a database and it turns out you do not have enough 64 KB pages, AIX may decide to steal one of those 60 megabyte pages, break it up to 64 KB pages to allow you to start the database. Unused 60 megabyte pages will not, so later on, after the database is running, will not be converted, and AIX will not, after the database stops, recreate those 60 megabyte pages. So be aware. Log SGA equals true. That's the other option when memory is pinned. Everything is pre-allocated to max size. I already mentioned the 60 megabyte page implication. And if you go back to the second slide I presented today, where you see the variable memory over time, I clearly illustrate the challenge you can run into here, leading to significant paging to paging space. And just to be clear, this is the DBA who can basically significantly impact the behavior of AIX. Because SGA max size is a simple Oracle inode.org parameter you can set. And if you're utilizing log SGA, which would drive 60 megabyte pages by default, if you set that incorrectly, you can cause AIX worst case to basically being dying of paging space. One of the reasons why I say DBAs have to talk to the sysadmins to understand, okay, what is the memory available, how it's configured before making changes to these critical memory parameters. Here, a quick summary of what page sizes we support and how we would typically recommend to use them in AIX. And from my perspective, the preferred memory page size to use with Oracle database is 64 kilobyte, which is used by default if you do not do the log SGA equals true. I would also suggest to utilize 64 KB pages for binaries, stack, text size. There is, at the end, I will refer to a white paper which has the necessary details on how to configure that correctly, which is in the context of an ASM or correct environment a little bit more challenging. As you can see, we can also support 16 gigabyte pages, which are called huge pages in the AIX environment. On Linux, huge pages are only 16 megabyte. They are available. We typically do not recommend to use them. Very little experience in that utilization. And if you look the last sentence, if you utilize it, I found that it will allocate 3 additional 16 gigabyte pages out of the box above the specified SGA max size, probably for PGA aggregate target. So you get an idea that you have to have a really large SGA and PGA and physical memory to see any benefits of using 16 gigabyte pages. And configuring them is also much more involved and not dynamic than all the other page sizes. So now switch over to CPU. Here, a quick graph you probably have not seen yet, illustrating the scaling of Power 8 with SMT compared to Power 9. So I actually did a small test with an OLTP database, driving heavy transactional workload against an S924. And you can see the scaling behavior from SMT1 to SMT8. The suggestion with Power 9 is really to utilize SMT8 configuration and not start out with SMT4 for Oracle databases, because SMT8 in a Power 9 environment provides significantly additional capacity and performance as compared to Power 8, where the benefit of SMT4 or SMT8 was a little bit of a mixed bag, depending on workload. On this slide, I will not go into it because of timing. Point is only Power 9 license factor is still 1.0, and it is now finally documented in the official Oracle core licensing factor table. If you want to talk further about licensing, shared processor pool, and those topics, we probably need to do that in a one-off separate. But this slide has a pretty good overview of what features you can use to optimize/minimize your Oracle licensing requirements. In the context of SMT and how processors are folded and unfolded, we have relatively new parameters called VPM throughput mode. And I added this slide to make you aware of, or to discuss a little bit what it actually means. If you go with the VPM throughput mode of 0 or 1, which is the default, and which is the old maximum performance mode, this is what you see on the left. You have your physical cores or virtual processors, depending if you're running dedicated or shared CPU, ALPA. But AIX will basically utilize the first thread, which I just label here primary. And if it needs more CPU based on usage, it unfolds another CPU and so forth, and only utilize the primary threads. And only when all the primaries are used, then it will use the secondaries. If we go to the tuned mode 2, AIX will utilize first the primary and then the secondary, and then unfold another core or virtual processor and so forth. And the same goes all the way through. So what is the impact on performance? The best performance you will get, of course, if you go with the quickest unfolding, so on the left, with the raw performance mode. But if you are not utilizing all the threads, then you may utilize, you will lose CPU cycles to the workload, or to the hypervisor. Basically, it comes in, schedules the logical processor, finds there's no work, and the logical processor is basically unscheduled. So you get the best response time, you get the best application throughput for low threaded workloads, but you have the highest physical CPU utilization. So if you have an environment where you have many LPARs competing for resources, this may not allow you to utilize the CPU resource in the server efficiently, but gives you the best application performance. If you go all the way to the right, you have the worst application response times likely, because you are sharing the same physical core and the resources, which are limited, between 8 different logical processors. But you are only utilizing, or you're best utilizing the resources of that specific core of a virtual processor. So worst application response time, but lowest physical consumed. So it's something, again, there's to evaluate in your workload how you distribute or how you configure this and try to get the best resource usage, still meeting your SLAs. Now back to the Oracle database story, what parameters are impacted by the number of logical CPUs, which are dynamic in AIX, SNT-CTL command, and you can, and the database dynamically adjust those settings based on those number of discovered logical CPUs. So CPU count reflects how many logical CPUs do I have. The DB writer processes are dependent on that number, and then the global cache service server processes in an Oracle RAC environment are also configured based on this. Degree of parallelism can be impacted by this. So you see the default degree for queries. You may want to adjust your parallel max servers based on logical CPUs. So it's something you need to evaluate. If you have more logical processors you can drive workload against, you potentially can increase the parallelism or the maximum parallel servers you can execute efficiently. And the cost-based optimizer in Oracle is, of course, impacted by how many CPU resources I have available, or the database believes it has available. And it may decide to change an execution plan if you change the number of processors available to the database. I already mentioned that for Power 9, I would suggest to start out with SNT-8 mode when you deploy an Oracle database into the airport. I would also suggest that you set the parallel threads per CPU to 1, so that you're not overloading logical processors with too many concurrent threads. Right? Remember, logical processor, if you're running SNT4, SNT8, you're already running 4 independent workload streams on the same physical core. And if you take the default of parallel threads per CPU equals 2, you're just doubling that already heavy workload, and it's likely will perform worse, at least based on our testing, than having just one parallel thread per logical processor. From a shared processor pool configuration perspective, if you run a capped shared CPU helper, your number of virtual processors should be next larger than the capping limit. Otherwise, you cannot even use the full capacity of the entitlement. If it's uncapped, then virtual CPUs are a hard cap on an LPAR, so you may want to make sure that you have sufficient vCPUs configured to meet your peak demand. And I already mentioned that typically number of vCPUs should not be more than a 1.5x to 2x the entitlement for efficient resource usage. If you're doing dynamic CPU LPAR changes, be aware that with 10G and 11G, you could only change the CPU count up to 3x of this CPU count at instant startup. So if you go from SNT off to SNT8, CPU count would not dynamically adjust to that new number. So just be aware, in 12C that is resolved, and at the bottom it's a pretty recent Oracle bug you want to be aware of in the context of logical processors and significant changes in logical processor numbers. Processor folding, I already talked a little bit about it. I have seen some workloads things, for example, like import of data into a database, parallel import, or very spiky workload being negatively impacted by default processor folding in AIX. So I typically suggest that to keep maybe one or two more processors unfolded than AIX would calculate based on physical CPU utilization. For Oracle RAC, it actually has to be set to 2. And the parameter to change would be the VPM_XV CPUs. A very recent discovery is that on P950 or E950, you may need to adjust the VPM fold threshold to a lower value to make AIX more aggressive with unfolding. We have seen that otherwise you may, with relatively low workloads, that AIX folds too many CPUs, and that significantly impacts the performance, or if you're in an ODP environment, your transaction rate. So if you're running on an E950, which I think are now available, then that may need to be changed, and I believe that is already being worked on as an APAR and will be officially included very soon. One other feature, very short, Power9 servers running maximum performance mode. This graph is a little bit strange graph, shows you how frequency over workload changes. The reason why I brought this up is if you're running a performance test in an environment, but you only run maybe a 10% or 20% part of the overall workload, and then you switch to production, which is a much larger workload, you may see that your frequency goes down with higher workload, or you will see, and therefore processes which are CPU frequency sensitive, means very CPU intensive, single threaded, may actually slow down more than you would expect because of the frequency drop under higher workload. So just be aware of that. Now switching to a complete different topic, and I'm pretty short on time, so let's see that I get through it. On a very high level, this is how I/O looks like in AIX if you're using JFS2 file systems, so logical volumes. You have your H disks, you have your PBUFs in the logical volume, volume group. You have your disk queues, which actually control how many concurrent outstanding I/O you can have via that H disk. You have your multipass driver, which then gets also includes where it gets routed to the fiber channel adapter. It could be a physical adapter, it could be NPIV in this case. And the adapters themselves also have, again, a command queue controlling on how many concurrent requests they can send against the storage subsystem. So typically what we tune on the disk side is a queue depth. As I mentioned, that is really how many concurrent I/O can I drive. And you need to make sure that the combined queue depth for your disks is capable of supporting your maximum concurrent I/O request rate. Note that you need to talk to your storage vendor before just increasing queue depth to the maximum of 256. There are storage subsystems which have limits on how many concurrent I/Os they can handle. And if you go above that limit, then they tend to just silently drop that I/O request and it has to time out in the operating system. So you can see 10-second I/O service times because an I/O failed and the database has to restart it. So very disruptive to performance. But queue depth is an important factor on how much I/Os you can drive. The other factor is maximum score transfer. How big is the maximum I/O you're allowed to drive via that H disk? The default is 256 kilobyte on AIX, especially in data warehouse workloads where you do a lot of large table scans. You want to get the maximum I/O size supported from your storage subsystem. I would suggest you get or set that to 0x100,000, which is basically the corresponding to 1 megabyte I/O size. That is also the default I/O size Oracle generates for table scans. On the fiber channel side, we have the NUM command elements. Basically, how many of concurrent I/Os can I drive via the adapter? The default of 256 I find very often significantly too low. So I regularly set that to 1024 or 2048. Again, talk to your storage subsystem vendor and please very carefully evaluate those APARs I'm listing here. That's especially important if you're using NPRV. So not physical fiber channel adapters, but NPRV. So there have been a number of issues in that combination. In the interest of time, I skip the rest here. You can just read on them. It's pretty straightforward to set. We have a number of support structures for I/O, and especially in the logical volume area and JFS2 command space. So with the VM/v command, you can determine, okay, am I running out of P-bus, for example, or file system buffers? I found a good article published by IBM talking about how you can determine if you're running out of, if you have problems, and what or how to increase the specific buffers to address any shortages. So in the interest of time, I decide, okay, just point you to that great article, and then should be pretty straightforward to address that. From historically, and it's probably now, hopefully, for most customers, really historical, DBAs tended to say, okay, I want to have my index files in one set of disks and my data files in another set of disks, or have that specific table or table space I want to have on a separate disk. That is not what I would recommend these days. I have seen way too many problems with hotspots and a lot of manual activity trying to address those hotspots with that approach. So what I call your new wisdom is really stripe your database object, means index and data files over as many physical disks as possible, and do not separate index and data files, for example. If you look at the ASM Oracle Advanced System storage management, it does the same. You have basically arguments, okay, 3 ASM disk groups, one for your index and data, one for your redo, and maybe another one if you're running Oracle RAC cluster. But Oracle's recommendation goes along exactly the same way, and they implement it like that. So do not separate out index and data, for example, any further. From a storage perspective, how would I typically lay out a database? So on the storage, we have disks depending on storage environment. You typically have hardware striping. You create LUNs from your storage, you try to separate LANs from, or allocate LANs from different set of disks. That is especially important if you utilize spinning disks, which have position latencies, this is arm movements, in the context of ASM or logical volume striping, because double striping can really kill your performance. So if you're now on a more current storage subsystem based on flash or SSDs, that is not really that important anymore. But if you're relying on spinning disks, this is still relevant. So LANs striped over a number of physical devices, presented to AIX as H disks, and then you stripe via software on top of all those H disks. That can be either ASM, this group, it can be AIX, this JFS2, or it could be GPFS. Here a little bit, a handy reference slide. Okay, what is volume, logical volume? How do all these pieces together? Main point is on the bottom where I show this small graphic. If you're utilizing JFS2, make sure that your logical volume under your database file system is not utilizing minimum spread. Because if you use minimum spread, there's a very high likelihood for hotspots and only a small subset of H disks actually being used by the database over time. And those hotspots typically wander around depending on usage over the H disks. Problem is, minimum spread is the AIX default. So if you do not take care and manually change it in SMID or SMIDI, you will end up with minimum spread. So this is just a reference slide. In the interest of time, I will skip over it. You can do striping with two methods for under a JFS2 file system. One is striping on the logical volume, and I typically recommend to utilize a 1 megabyte strip size if you utilize logical volume striping. Beware that future growth, so if you run out of space of a LAN being part of a striped logical volume, future growth can be a little bit challenged if your SAN does not support dynamic LAN size growth. So I just leave it at that. If you have follow-up questions, you can send me an email on that. The other option is PP striping, which is basically physical partition size. For databases, you would create your volume group with 8 megabytes, 60 megabytes, maybe 32 megabyte PP size. I would not go about that because then you end up again with small database objects sitting in one PP. One PP is mapped to one physical LAN of one H disk. So if that object happens to be hot, you end up again with hotspots. That's the reason why PP size should be relatively small. So for smaller databases, I'm seeing PP striping as a viable option. For larger databases, I typically, if you go with JFS2 as the underlying file system storage, then I utilize logical volume striping. But with 1 megabyte strip size, not really, not with small block sizes. In Oracle environment, you have a number of different files, flashback log files, database files, control files, and so forth. And here just a quick overview of what you can put those files on. JFS2 supports all, GPFS as well. If you're running ASM itself, you can basically put everything into an Oracle ASM disk group except the Oracle binaries. With ASM cluster file system, which is a clustered file system on top of ASM, available as 12.2, you could put all the files or file types within ACFS, but there are restrictions, and if you really want to go down that route, you want to read up on them. From a practical perspective, we have seen some challenges with memory management in AIX and the ACFS file system usage, the caching control. So my recommendation would be not to use it. I would stick with ASM, or if you want to have a cooked file system, JFS2. Key point in database is always improving your I/O performance. And to improve I/O performance, the first thing is don't do the I/O at all. So the biggest bang for a buck is quite often look at your SQLs. Do they drive unnecessary I/O? Is the execution plan your database is driving really optimal? Can you do anything there? So that's the first one. It's the most difficult potentially to tune, but that's typically the biggest bang for the buck. The next step is increase your database cache hit ratios. So I mentioned database cache in the SGA. Can I increase that cache size to keep at least my hot accessed working data set in that cache? That would be the next approach to minimize physical I/O. Third one is Oracle in memory. And I have one slide, I should hopefully be able to get to it, which illustrates what the impact that can have. So from a host level striping, I already mentioned ASM stripes by default. With single instance, you can use JFS2, and there you would utilize logical volume striping, 1 megabyte, or you could use physical partition striping. And then the last level is really, the alternative is GPFS, which I think is the old name. But it's a cluster file system which stripes automatically under the cover like ASM does. And you can see I'm scrolling through, you will get all the slides, and there's a lot of material still left. I already mentioned the buffer cache here on this slide, a quick example where customer started out, had a way too small buffer cache, and the database had a lot of I/O weight. So increasing the buffer cache, in this case, very significantly, as you can see, brought the I/O per second from over 300,000 down to 50,000, and I/O wait time 91% reduced. This is, of course, an extreme case. Typically, DBAs already are aware of this, but if not, you want to definitely evaluate, are your database cache hit ratios within the expected range for your workload? If you're utilizing JFS2, I want to talk a little bit about direct I/O, concurrent I/O, so everybody is aware of what it actually means, what the implications are. In a default configuration, you mount your JFS2 file system standard way. You have an inode lock sitting in front of your file. So every time you have a writer, only one writer gets access to your file. Every I/O goes via the AIX file cache. Now, if I go to direct I/O, I remove the AIX file cache out of the I/O stream. So the database does a write, but it can only do one write at a time because the inode lock is still active. Now, if I have concurrent I/O configured, so JFS2 with file system I/O options equals all, then the database writers can, in parallel, write to the same physical file. The database is responsible for controlling what specific blocks within that file are changed, so that not two different writers change the same database block. So CIO is a very specific mount option which completely removes operating system access control and should be therefore only be used for applications like an Oracle database, where the database or the application controls the writers, who can write to what block in a file. And as you can see here in this picture, normal mount, you have double caching. So the data is potentially in the database cache and the AIX file cache. Whereas with concurrent I/O, the database is only in the database buffer cache, and there's no double caching involved. That's why concurrent I/O, especially in OLTP workloads, can make provide very significant benefits. And if you don't have to support a file system cache, your database cache can be accordingly increased. So I skip this one. From a configuration perspective, how are database files accessed, which is important from a configuration perspective, whereas concurrent I/O and direct I/O is used. And this slide gives you an overview. So I'm now on 64 of what typical I/O sizes are and what specific settings you should utilize. The one I see most problems with is the location where you put your video log and control files if you're utilizing a cooked file system like JFS2. Video and log and control files are potentially driving 512 I/O byte IOs. JFS2 default block size is 4 kilobyte. You could end up with very significant I/O overhead if you do not correctly configure JFS2. So for the location where you put your video log control files, you should utilize a JFS2 AG BLK block size of 512. The only exception is if you utilize 4K sector disks. And I hope that after my previous discussion about concurrent I/O and direct I/O, do not use concurrent I/O, direct I/O for anything with Oracle binaries. Because if you do that, you will end up with data corruption. It's really just for the data, for the file systems, supporting your data and video logs and those database files. I'll skip the file system requirements because the nice thing is, since with AIX I, they are already set that I typically do not need to change it. Please note they highlighted APAR, which can impact how quickly AIO servers are started. For reference, I give here on slide 67 AIX commands you want to utilize in ASM environment. If you utilize ASM from a system admin perspective, you want to rename those devices, you want to lock those devices so that you do not accidentally create a volume group utilizing those HDisks. Because if you do, that create volume group or mkvg command will override data on those disks ASM relies on. So best prevention is rename the device to make clear that it's an ASM disk, and locks the device with a description of why did you rename it and lock it, and provide him an example.
So Ralph?
And yeah, I have one slide, and I think I stop.
Okay. Yeah. All right. Go ahead and do that and wrap up. And
yeah, correct. So, so what I already mentioned, the in-memory impact, and I just want to provide this here as an overview. In the raw format, this is 8 concurrent the ITAB queries running against my Oracle database. And you can see that I'm CPU bound. I ran for a long, long time, had a high I/O throughput requirement, and I read about 12 terabytes of data from disk during that time period. I have the same data in memory in the system. I ran the same 8 concurrent users, same query, and you can see that I'm basically not doing any physical I/O as expected, that it's much, much faster, and only have, again, utilize high CPU. If I rerun the same query again, I would, with the raw format, read again 12 terabytes of disks from disk each and every time, whereas with the in-memory, I would still see a very, very little read impact and just CPU, and of course being much faster. So I'm seeing I'm running out of time. I got a really big red flag from Joe. So I appreciate your time. You will get the additional slides. There's a few more. The one I want to really highlight is this one here. If you're not familiar with W3, look at the technical sales library documents, especially the one on the top, is consistently updated, has a lot of good tips and recommendations, and also lists current relevant APARs, current relevant SRs from Oracle you want to be aware of and apply as required. And I leave this here at the bottom. We have an option of analyzing a customer's performance data from Oracle AWR data and provide a pretty detailed and recommended report back to the customer. This is a free of charge offering. There are some limits, but a business partner or the IBM seller, you could contact them to request one of these reports. And here you see a sample of what kind of information and feedback you can receive or will receive with that report. And Joe, I think with that, I'll stop and
okay.
Get back to you.
Okay, so just a couple of wrapping up comments. And guys, first of all, sorry we didn't get through all the material here. As Ralph mentioned, there's some stuff that you can contact them for. Feel free to contact Ralph, or you can contact me, and I'll pass it on. If you want more information on anything, then we'll get you set up. I don't want to leave anybody hanging that they didn't get everything that they need. Replay will be up on the wiki site. The presentation materials are there now. We'll put in a kind of an expanded presentation materials. Next month, we're talking about VIOS. We have some updates to the VIO server, and so we'll be covering that in October. If you're at TechU, I mentioned TechU, I'll be there. I'll have stickers and some more TechU Power Systems bug t-shirts to give away. So if you're there, come find me, and I'd love to meet you and give you a t-shirt. With that, we're going to wrap up for today. Ralph, thank you so much. Really sorry that we were short on time here. I guess maybe I should have just scheduled 2 hours or something, but thanks so much for all this great material. And Tim and Neil, thanks so much for answering questions. I see that our questions log is, our questions list is very short because of that, and I really appreciate that. That helps a lot. With that, everybody have a good month. See you next month.
Thank you, Joe.